All right, so we're going to start looking at 3 dice, which we're going to have to handle a little differently than the 2 dice problems, because the 2 dice problems, there's 36 possibilities, not too hard to list them out, and a good way to organize them we saw is in like an addition table or a multiplication table. But when you get to 3 dice, you can't put it in a 2-way table for one. You'd have to put it in a 3-way table, which would be 3-dimensional, and that would be, it's not easy to put on paper. Also, there's quite a few possibilities. In fact, how many possibilities are there? 216, because each die has 6 possibilities, and 6 to the 3rd power would be 216 ways. So which one did you guys do? You did number 15? So we already did 15, and we came up with 5/9. Okay, so we already got that one down. And what we did there was 6 times 5 times 4 over 6 times 6 times 6. Reduce that. We got 5 out of 9. Okay. So let's take a look at 14. 14 says if we have 3 standard dice that are rolled, what's the probability the resulting sum is less than 6? So what's the lowest sum possible? 3, right? If you roll 3 dice, the lowest sum you can get is 3, right? And so, so if I want a sum of 3, then that would be a 1, 1, 1. And that's the only way to get that, right? And so what I'm doing right now is I'm listing out. Sometimes the only way to do these problems is just to list them out. And if there aren't too many to list out, why not do that, right? And so that's what I'm doing right now. Sum of 4, what's a possibility for that? Okay, a 1 and then a 2 and then a 1, or 1, 1, 2, or 2, 1, 1. So 3 variations of the same case. But besides getting 2 1s and a 2, is there any other way to get a 4? A sum of 4? That's it, right? And then we want it less than 6, so there's only one more possibility, or one more sum to consider, which is 5. And so how can we get a 5? 3, 1, 1. 3, 1, 1 works, right? Okay. And there's different variations of 3, 1, 1. So 1, 3, 1. And 1, 1, 3. Is there any other way? 2, 2, 1. And you can move that one around as well. All right. Are we missing anything, or have we got them all? We're trying to be thorough. We're trying to be organized to make sure we don't miss anything. Does it seem to you that we got it all? Okay. So then at that point, we're going to count how many we have. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways out of 6 to the 3rd power. We've seen that in the other problems already. So 216 possibilities. We can reduce this. We divide top and bottom by 2. Get 5 out of 108. And we got our that's our probability. Okay. So the strategy there for the numerator was just to list them out. For the denominator, we were using the basic counting principle. Okay. Number 17, suppose 3 standard dice are rolled. What is the probability their product is prime? So again, we can't create a multiplication table with 3 things, right? So, and as you did with 2 dice, we can't do that here now. So let's resort to the most basic ways. Just let's list out what can happen. So we try to orderly pick a prime that we can get. What's a prime number that we can get? What's that? 1's not prime. The first prime number is what? 2. So 2 is your first prime, and it's the only even prime out there. So if we get a 2 and we're multiplying 3 numbers or 3 integers together to get 2, we know what those 3 integers have to be. There's only, what are they? 1 times 2. But there's variations of that, right? 1, 2, 1, and 2, 1, 1. So there's 3 different variations of the 2 1s and a 2, and that's the only way we can get a prime number of 2. What, are there any other prime numbers that we can end up with when you multiply the 3? And so what would that get? What would the 3 numbers have to be? 3, 1, 1. And you can say 1, 3, 1, and 1, 1, 3. Any other primes? 5. And that's going to come from what? 2 1s and a 5. Okay, any other primes that we can get? Can you get a 7? Can't get a 7. And I mean, with 6 sides, you can't get a 7. If you had more sides than 6, and there are dice with more sides than 6, but this is it, right? So how many ways? 9 ways out of 216. And we can reduce that. 9 is 3 times 3. 216 is 6 to the 3rd power. It's going to be 1 over 24. Okay. So again, the strategy on 17 was, for the numerator, was to list out the possibilities. And that would probably be a good way to go about it. There's only 9 possibilities, smaller problem to do. 18 says, if I roll 3 dice, what's the probability the sum of the 3 numbers is even? Sounds a little bit more complicated, right? You want all 3 numbers to be even. And how do you start with this one, right? Well, we have it nailed down how to do the sum of 2. Okay? And when you add 3 things, you have to start with adding 2 things, right? It's a binary process. And so what I would do is list out what the possible sums are for 2. We create that addition table like we've done. Okay, so if I add, so I'm going to add 3 things together, but if I add the first 2 together, these are my 36 possible sums. And so we're going to add those together with the 1, 2, 3, 4, 5, 6. And some answers are going to be even and some are going to be odd, right? And so you got the 2 plus the 1, 3 plus 1, 4 plus 1, and you go through all 36 and multiply those with the 1, or add them with the 1, sorry. And some of those will be even, some will be odd. You can take all 36 of those and add them with the 2. Some will be even, some will be odd. Take all of them and add them with the 3. Some will be even, some will be odd, right? And then we want to count up, well, how many of those eventually were even? So let's just think about when we add them with the 1. Which of these numbers, when you add them with a 1, will be even? Okay, so if you take all your odd numbers, now how many odd numbers are there out of that 36? Okay, so we have 18 odd numbers and how many even? 18 even sums, right? And if we look at the 36, and you can count them and so on. So anyhow, when we take and add them with the 1, you're going to have 18 odd numbers, and when you add those odd numbers with the 1, you're going to get 18 even numbers, or 18 even sums. Okay, now if you take all 36 of these and add with the 2, see where this is going? Which of the 36, when you add the 2, will be even? The evens, right? So we got 18 evens, so you add them with the 2, you still get an even number, so we have 18 after we add them. Okay, then with the 3, which numbers, or what kind of numbers would we have to add with 3 to get an even sum? Odds. God bless you. But there's 18 odds, and so no matter what happens, there's 18 that we get out of each one. Okay. Can you see what the probability is going to be? Yeah? It's going to be half. Half of them will be even, half of them will be odd. But let's continue this process. So we have 18 times 6 out of 6 to the 3rd power. And start reducing this. We get 3 out of 6, which is 1/2. Okay. So it starts out being a challenging problem, but one strategy here is to get the sum table for 2 dice, and then think about, okay, if I take those sums and add it with 1 dice, it's a little easier to digest and think about. Yeah. I'd love to hear. How'd you do it?
The only way to get it even is to odd numbers or to all
Okay, so if you're adding 3 numbers, the only way to get even is to either add 3 evens, or you can add 2 odd numbers with an even number. There's no other way to get an even sum. Okay, keep going. Mm-hmm.
then 3 of them are odd, 2 of them are even.
Okay, so you're counting. How can we get this? Is that what you're saying? Okay.
Or so the first one could be any of the 6 numbers. Then make an even number.
Oh, okay. So for the first one, you can have any even or odd. Okay. Times. Okay.
And you get 108.
Okay. So let me see if I can follow you here. So this could be even or odd, right? This could be even or odd. But no matter what, you're saying this third one has to be even? Because let's say, so if we had an even, odd, even, would that work? You see that it looks like, and I'm just thinking through it, right? So that one wouldn't, in that case, there's a little hole. Okay, say that one more time.
That one,
The first one or the middle one? Okay. Uh-huh. Okay. So if this was an odd, then you'd have an odd. So you'd still have 3 possibilities. Okay, so it really doesn't matter what the first two are. Whatever the first two are determines if the last one has to be even or odd. And there's 3 evens and there's 3 odds, so it works. Okay, now you're making sense, and I'm good with that. Does that make sense to you guys? Okay, and so that's how you get the 6 times 6 times 3, which would be the same numerator, and it would work out. That's good. Okay. All right, number 19. A fair 6-sided die has 2 red sides, 2 blue sides, and 2 yellow sides. If the die is rolled 3 times, what's the probability that each color is rolled once? Anybody give this one a try? Okay. You want to share?
Roll the die 3 times, and we have a 6 outcome each time. So the denominator would be
Do 16 again. We're all good with that. Okay. So numerators, that's the tricky one, right? Now, how do we get the numerator?
the first wall, any of the 6 colors.
Okay, so any side can happen on the first one. There's 3 colors, but there's 6 sides, right? So you're saying any side can happen. Okay.
4 more.
It's only 4 sides that can come up, because if we picked a color like red or green, or you can't, that color cannot repeat, so there's only 4 more options, 2 of one, 2 of the other. Okay, times, and when you multiply that together, well, probably don't need to, huh? Because that's the numerator. It's 48. Okay, and then we can reduce this to what? That makes sense to you guys? It's a great way to do it. There's not a lot of work, and it works out good. Did anybody try a different way? Here's another way. If you didn't think through this, you could have listed out, well, I can get a red, blue, yellow, and if I get it in that order, how many reds are there? 2. How many blues are there? 2, right? And how many yellows? 2 options. But then I could rearrange this, just like I gave you 3 letters before. How many different ways can you arrange? How many new words can you make with 3 letters? You could do red, yellow, blue, red. It's 3 factorial, right? So and each one's going to have the 2 times 2 times 2. And so if I could list them out. There's 6 different ways, or I could just multiply it by 6. And notice if you multiply that together, you end up with 48 as well. So there's different ways to count them. You just got to be careful how you count them. I like your way better, Chase. It's more concise. But if you didn't have that idea, that's okay. What's important is that you think through every possibility out there somehow. We did 21. We just divided 2016 by 3 and got 336. Okay. But number 20, you roll a die 3 times. What's the probability you get exactly 2 6s? Anybody else try this one besides Chase? Chase has answered a couple already. Want to give you an opportunity yeah. Okay, and so I understand the denominator, right? Because there's 3 sides, but why 1 times 1 times 1? Why'd you say never mind? Okay. You realize you're missing something? Okay. It's all right. We'll back up. So we need to somehow count how many ways you can get exactly 2 6s. Yeah. 1 times 1 times 5. Okay, and that's gonna be you guys see why 1 is that's the first one's a 6, the second one's a 6, and the third one's not a 6, right? And say there's 5 different ways. And we can list them out. You got the 661, 662, 663, 664, 665. Are we missing anything? That's definitely good what you did. Are we missing anything though? What? Okay, so there's another case. What if we have a not, the first one's not, and the last two are? And so you're going to have 5 times 1 times 1 ways. You see that? Are we missing anything, or did we hit them all? Okay, so the first one could be a 6, the second one's not a 6, the third one is a 6, and so that'd be 1 times 5 times 1. And so when we add those, we get 15 ways. Have we hit them all though? Yes. Now we have. And so we got 15. So 3 times 5 is 15, and we reduce this, and we end up with 5 out of 72, which is A. Now, did yours end up, when you did 5 over, did it end up being one of these or none of these? Ended up being none of these. Okay. Okay, but you were close. You were very close, and you were thinking good. It's just the other variations, right? These are tricky, but the more practice we have with them, the better we get. Okay, so this next part, like I said, a strategy that can really come in handy where you can make a really difficult problem a lot easier. And doesn't work on every problem, but when it works good. Okay. And to give you some background, we're going to start with a simple problem. So let's say you roll a die, and A is the event of getting a 2. So I could write this. A is, in set notation, a 2. Okay. What is the probability of A? 1 out of 6, right? There's one way out of the 6. Okay. What is the complement of A? Everything else, yeah. Which would be a 1, a 3, a 4, a 5, or a 6. And so what would the probability of the complement of A equal? 5 out of 6. And so if we take the probability of A and add that with the probability of the complement of A, what will we get? 1. And in fact, no matter what event you choose, if you take the probability of that event plus the probability of the complement of that event, you will always get 1, which should make sense because this is saying, hey, what's the probability this happens plus the probability this doesn't happen? 1. One of those is going to happen, right? And if I subtract the probability of the complement, I get this formula: probability of A is equal to 1 minus the probability of the complement of A. And that's what we call our complement rule. Well, actually, I put it the other way, but both work, right? And so let me illustrate a couple problems where this is nice. So here's the first problem I put together. It's not in your notes. but I want us to take a look at it. So an experiment consists of throwing 6 fair coins, and we want to find the probability of getting at least one tail. Okay. So let's let A be that event of getting at least one tail. So A could be, what does at least one tail mean? What's that? Means you can get one tail. In this context, what else could you get? Could you get 2? At least means you could get more, right? All the way up to what? Okay, and so then we have to look at each case. So if we get one tail out of 6, that could be one. The first one was tails, and the others weren't. And then, but that's not the only way, right? What else could happen? The second one could be tails. And then how many would fit under that one tail category? 6, right? And then we could look at 2 tails. A little more complicated. The first 2 could be tails. And then maybe the first one's heads and the second one's tails, and then maybe 2 heads and then a tail and then a heads, and you're moving things around, right? And let's think about counting. How many ways can this happen? Think about what you've learned with counting. There's a couple ways to attack this one, and 30. How'd you get 30? Okay, 6 times 5. It's a little different than that. Remember when we had words and I asked you how many different ways can you arrange those letters? You actually had one on your quiz you just took, right? You remember how to handle that? Think of this as a word, the TTHHHH. We would say, well, there's 6 letters, but we have repeats of letters, right? And we have 4 H's, and we have 2 T's. And so we could say, well, then that's going to be, work that out. And we end up with 15. So you're close, huh? You said 30, but it's 15. And by the way, I don't know if you noticed the notation here. This is actually equal to 6 combination 2. Okay. So you have to, but that's just with 2 tails, and then you got 3 tails. You see where I'm going? This is complicated to count all that stuff. And so you may want to think, instead of approaching it through the front door, let's try the back door. What would the complement of A be? No tails. And let's just try that one out. Okay, we have no tails. We could have, there's a case with no tails. And then what else? That's it. There's only one. Much easier to work with, right? Much easier to work with. And so let's figure this out, because the probability of A is equal to 1 minus the probability of the complement of A. And this is much easier for us to find in this case. Okay, and so that's going to be 1 minus 1 out of what? We need to know what our denominator is going to be. So we got to count sometime, right? Well, if you're throwing 6 coins, how many different possibilities are there if you were to list them all out? So first one, you have 2 options. Second one, you have 2 options. Third one, and so on. So you end up with 2 to the 6th power, which is 64 ways. Okay? And so this is going to be 64 out of 64 minus 1 out of 64. Get a common denominator. And we finally get our answer, 63 out of 64. So we can get it the direct way, which is the side on the right. We'd have to go through all of these cases and add them up, and we would get 63. But it would be a lot more work. And so sometimes the complement is much easier to tackle, and keep that in mind. Always say, hey, if you're into like a big mess, not that you can't work your way through it, but just stop for a second and say, is the complement going to be easier here? Because if it is, let's go that route. Okay. Let's try one more. An experiment consists of throwing 7 fair coins. Find the probability of getting at most 5 tails. I want you to try it before I help you out. Okay. Okay. So on B, if getting at most 5 tails is what we'll call it, event A. All right. Give me a second. Then what does that mean? At most 5 tails. So A would mean the event of getting what's the smallest number of tails you can get? 0. So no tails. And then you can get 1. Up to what? 5 tails. Okay. And so this is kind of like the last one where you're going to have to, you have 6 possibilities there. No tails, 1, 2, 3, 4, 5, and 6. And so we're getting a little smarter here, and we're going to think, well, what's the opposite of that? 6 tails, 7 tails. Okay. So it's not as easy as the previous problem, but do we want to try 6 different options and list them out? We can. Or do we want to go with 2 options? 2 sounds better, right? So a little less work. Again, the complement is not always easier. In this case, it is. And so 7 tails, there's only one way to do that. 6 tails, well, you have 6 T's and an H, right? And how many different ways can you arrange those? 7. And you could list them out. So you can move the H in 7 different places, right? You can reason through that. Or you can think of it as a word. You got 7 factorial, but I got 6 repeats of a T, and so that comes out to 7. There's different ways to come up with that. But you can count 7 ways for 6 tails and 1 way for 7 tails. So you add those together and you get a total of 8. And so the probability of the complement of A would be what? 8 out of 100, where did 128 come from? 2 to the 7th power, is that what you guys are doing? Okay. And so 8 is 2 to the 3rd power, or 2 to the 7th power. Remember, if you have a common base, you can subtract your exponents. So this is 1 over 2 to the 4th, 1 out of 16. You can use those rules for these numbers if you want. Okay. So that's the probability of the complement of A. But we don't want that. We want the probability of A. So what's it going to be? 1 minus 1/16, which is 15 out of 16. Okay. So I'm teaching you something we call it the backdoor approach, using the complements. It doesn't always work with every problem, but a lot of times it does. And the key thing you want to look for is when it has the at least or the at most, Those are kind of trigger words to think, what's the complement of that going to be? Because oftentimes it's a lot easier and you can use that. Okay. So I'm going to stop right there.